Another really important concept in this world is what's called the limiting reactant. All right. And in a limiting reactant situation, you have two or more reactants, and almost inevitably, one of them is going to limit how much product you can actually make. So the limiting reactant. Now, before I go into how we actually can calculate this in chemistry, I want you to look at that upper right-hand picture right there. Let's say that you and your friends are back at your apartment or house, wherever, and you all are really hungry and you want to make a cheeseburger. All right. Now, I'll be honest, I'm a vegetarian, so I'm going to say they're veggie patties, but you can use whatever you want, meat things, whatever. Doesn't. Anyway, you look in your refrigerator and you have 3 veggie burgers, patties, in your freezer. You got 6 buns, hamburger buns, and you have 12 dozen slices of cheese. Okay. Now, remember that your ultimate burger has a bun, it has a patty, and it has 2 slices of cheese. So if you looked at just the buns, you'd say, hey, we can make 6 of these ultimate burgers, no problem. And you have 12 slices of cheese, and each of them takes 2 slices. So you could also say, looking at the cheese, yeah, no problem. We can make 6 of these burgers, no worries. But when you look in the box with your hamburger/veggie patties, oh, wow, you've only got 3 of them. So the hamburger patties here are limiting how many of these ultimate burger things you can make. If you only have 3 patties, that means you can only make 3 burgers. Now, the buns would predict you could make 6 burgers, and so would the cheese. But those are false. You have more of those reactants, if you will, around than you have the patties. So the patty here would be the limiting reactant. It's limiting how much product you can make. And the buns and the cheese are called excess reactants, all right? They are going to predict that you can make more product than you actually can because of those darn patties. So at the end of your reaction, all right, you'll have 3 of these ultimate burgers with a veggie patty, 2 pieces of cheese, and a bun. But you're also going to have reactants left over, 3 buns and 6 slices of cheese. So that's kind of the idea. Money is another good example that you can use of a limiting reactant. I think all of us want fancy cars or, new Xbox or whatever is really cool in your world. Okay. And I'm not very hip, so I probably don't know. But the money almost always, of course, limits how much you can purchase. So money is our limiting reactant. That's kind of another idea, but I kind of prefer this garden burger or veggie patty idea a little bit more. So let's look at some examples of how this really is affected in chemistry. We have here 2 boxes. It's showing the reactants before and the products after. And if you look at this carefully, the blue atoms are nitrogen and the red atoms are oxygen. Now, in this reaction, it's going to take 2 NOs and 1 O2 to make 2 NO2s. So on the right-hand side there, these little triangle things, those are NO2s. The blues in the middle, the reds are on the outside. So an NO2. So you can see here you've got an NO2 where I underlined. There's a second one right there, and a third one, and a fourth one. But look there. Got O2. So one thing I want to point out is that for questions like this, if it asks limiting reactant, excess reactant is always going to be the part that's left over. You don't have any NO, you have NO2, but you do have O2 left over. So right away, the part that's left at the end, that's going to be the excess reactant. And in this case, you only have 2 reactants, O2 and NO, so that means by default, the NO, the other reactant, is going to be the limiting reactant. If you look on the left-hand side, you have 1, 2, 3, and 4 NOs. All right. So 4 NOs seems like it would be bigger than, I'll use a different color, 1, 2, 3 O2s. So it feels like 4 is bigger than 3. But darn that ratio. It takes 2 NOs to make 2 NO2s, but O2 only takes 1 of them. So you can see there what's happening. Those 1, 2, 3, 4 NOs make 1, 2, 3, 4 NO2s. And in the process, they'll use one O2 each, but we have 3 of them. O2 is left over. So always look, in this kind of type of problem anyway, if you have O2 left at the end, O2 is your excess reactant. And whatever else you had, in this case NO, it's no longer present at the end, that's going to be your limiting reactant. So you can look at it visually to see what's going on.
For this demonstration, we put 3 different amounts of zinc into the same amount of hydrochloric acid. At the end of the reaction, there is still some zinc remaining in the flask on the left. The reaction on the right did not generate as much gas because there was an insufficient amount of zinc. In the center reaction, the balloon inflated fully and all the zinc was consumed.
These 3 flasks represent the 3 types of situations that chemists can run into. And in the middle right there, you have a perfect ratio between the zinc metal and the HCl. So you can see up there in the top, this is the reaction that's happening. It's zinc plus 2 HCl makes zinc 2 chloride plus H2 gas. And H2 is a gas, by the way, it'll be important. So in the middle, you don't have any zinc metal left. Like you can see, all the metal's gone. And your balloon is completely filled up. That's the hydrogen gas, and that means you had just the right amount of HCl. Now the left-hand side, notice how there's zinc left over in the bottom. You can see the metal. So that means that zinc is the excess, but the balloon is filled up, and the H2 comes from the HCl. So we would say here that the HCl on the left was the limiting reactant. You've got zinc left over, the HCl is gone. On the other hand, on the right-hand side, there's no more zinc left. All the zinc is gone. And you can see there that the balloon didn't totally fill up. So what that tells us then is that on the right-hand side, the zinc was the limiting reactant, and we didn't use up all of the HCl. So these are the 3 types of situations you can run into. The middle one is kind of what we look for most of the time. All the reactants are used up. You'll have basically then just pure products. But a lot of times, you will have something like the left or the right, where one of the reactants is gone and the other reactant is in excess. You can visually see on the left-hand side there that there's zinc left over, so that means zinc is excess. HCl was the limiting reactant. On the other hand, on the right, there's no zinc left. Your balloon wasn't totally filled up, so the zinc is the limiting reactant, and the HCl is as an excess. We haven't used it all up. Here's some actual number amounts going on. Now, in all 3 of those flasks, there were 0.100 moles of HCl, all right? And every 2 moles of HCl, you would need 1 mole of zinc. So what that means is that if you have 0.100 moles of HCl, half of that would be 0.05. So the middle part, there's no limiting reactant. You have stoichiometrically balanced amounts of zinc and HCl, so they're perfect, all right? And there's the grams of HCl, by the way, that were used, and there's the ratio on the bottom. But anyway, on the left-hand side now, you have you can see that the zinc is quite a bit bigger than the HCl. Like we should have 0.05 moles of zinc and we have 0.107, so that's quite a bit extra. So the limiting reactant on the left was the HCl. On the other hand, on the right, HCl is still the same. We have a lot less zinc, so all the zinc is used up. There's HCl left. That's why in this case, then the limiting reactant was the zinc. It was all gone, and the balloon wasn't totally filled up, so we didn't use all the HCl. So these are just different examples. It's all based on moles, all right, and you can figure that out using a ratio or using the method I'm going to talk about here in a little bit. Let's imagine that we combine 3 moles of H2 and 2 moles of chlorine in this reaction, which is 1 H2 and 1 Cl2 making 2 HCl. The question is, what's the theoretical yield of HCl? Now, here's something that's really tricky sometimes in chemistry. This kind of question gives you 2 reactant amounts, but it doesn't say anything about excess or anything like that. So these kind of problems should scream limiting reactant for you. And you should really check out both H2 and Cl2 to see which one is going to give you the least amount of HCl, because the least amount is all you're going to get. Remember back to the garden burgers? There were like 6 buns, and it looks like there'd be 6 garden hamburger patty things? No, because we only had 3 patties. We could only make 3 buns. So you always look for the smallest amount. So what we're going to do is use essentially a stoichiometric ratio of the balanced reaction. It's going to be 2 moles of HCl per 1 H2 or 2 moles of HCl per 1 Cl2. So you take both of those initial amounts, 3 moles and 2 moles, 3 moles and 2 moles, and you use the appropriate reaction ratio. It's always 2 to 1, but you're going to have different reactants on the bottom. And lo and behold, you get 6 moles HCl from the H2 and 4 moles HCl from the Cl2. Now, only the smaller amount is possible. You don't have enough chlorine, in this case, to make more than 4 moles HCl. You certainly don't have enough to make 6 moles of HCl. So this kind of process tells you 2 things. First of all, 4 moles of HCl, that's the theoretical yield. That's the maximum HCl you're going to make in this particular process. You cannot make 6 moles of HCl if you only have 2 moles of chlorine. All right, that's just not going to happen. So chlorine here is the limiting reactant. It's letting you create less product than the H2 will. H2 is good to go. It wants to make more, but the chlorine, it's used up before you can make that 6 moles HCl. So chemists would call the chlorine the limiting reactant, and we would call H2 the excess reactant. And you don't want to tell your boss, for example, that you could make 6 moles of HCl in this case, because at the maximum, using 2 moles of chlorine, you can only make 4 moles of HCl. This is the value of knowing about the balanced reaction and how to find which reactant is limiting and what the actual theoretical yield will be. Here's a kind of question you might see. In this question, we're making ammonia, NH3, from nitrogen and hydrogen. But in this version of the problem, you have 10 moles of N2 and 25 moles of H2. And the question is, what is the limiting reactant? And it gives you N2, NH3, or H2, or they could be balanced, stoichiometrically balanced. Okay, so first of all, in this problem, there's no way that it's going to be answer C, because NH3 is a product. Limiting reactant will only be a reactant, things to the left of the arrow. So the answers will be N2 or H2, or if they happen to be balanced, it could be answer A. So the way to figure this out is just to go figure out the ratios needed to turn them into ammonia. So for example, for nitrogen, we have 10 moles of N2, 1 N2 will make 2 moles NH3, so 10 times 2 over 1, we can make 20 moles of NH3 from N2. And it feels like 25 moles of hydrogen is a pretty big number compared to 10, so it might be tempting just to say, it's probably going to be nitrogen. But really, you should check it out. So 25 moles of H2, you would use the ratio. You'd have 3 moles of H2 on the bottom because of the 3, and you'd have 2 moles of NH3 on the top because of the 2. So 25 times 2/3 would be the ammonia amount that you can make from hydrogen. And sure enough, when you do that, you'll notice that the ammonia from the H2 is less than the ammonia from the N2. And that feels weird at first because, wow, 25 moles of H2, that's a lot more than 10 moles. But those ratios have to be considered. And 25 times 2/3 is a smaller number than 10 times 2 over 1. So in this case, we can only make 16.7 moles of NH3. That's the theoretical yield of ammonia. And H2 is the limiting reactant. It's limiting how much NH3 we can make. N2 would be called the excess reactant. So back to that version here where H2 and Cl2 are making 2 HCl. Here the question says, what's the theoretical yield of HCl if 6 moles of H2 and 4 moles of chlorine are mixed? And in this problem, you do the same thing. Start with either H2 or Cl2. You'd have 1 mole of the H2 or Cl2 on the bottom and 2 moles of HCl on the top. Well, 4 moles of Cl2 times 2 over 1 would make 8 moles of HCl. If you did it from hydrogen's perspective, 6 moles H2 times 2 over 1 would make 12 moles. So 8 moles of HCl in this case would be the theoretical yield. It's how much HCl we should be able to make. So in this version then, chlorine is the limiting reactant and H2 is the excess. So it just depends on the ratio of chemicals, and you kind of have to figure this out each time. But here's the punchline. If you see two reactant amounts, moles of H2, moles of chlorine, and they could be grams of H2 and grams of chlorine, but these kind of problems should scream limiting reactant to you. You've got to check both reactants to see what's going on. In this reaction, aluminum and chlorine are making Al2Cl6. It's a dimer, two pieces of aluminum chloride, AlCl3, coming together. And aluminum does this. We'll talk more about why in a little bit. Well, let's say that we mix 5.40 grams of aluminum with 8.10 grams of chlorine. How many grams of Al2Cl6 can you form? And the very best way to do this, grams to moles to moles to grams. We're going to start with aluminum. We're going to turn grams of aluminum into moles. 2 moles of aluminum for every 1 mole Al2Cl6, and we'll multiply that by the molar mass to get the grams of Al2Cl6. You do this kind of process for both reactants to see what's going on, and the smaller product will be the theoretical yield. So let's look at how you would do that. Here's the math for both the chlorine and the aluminum, okay? So 8.10 grams of Cl2, you would turn it first into moles using the molar mass of Cl2, 70.9 grams. Then the balanced reaction says 3 moles of chlorine are needed for every 1 mole Al2Cl6. You would multiply that by the molar mass Al2Cl6, which comes out to be 266.4 grams per mole, and it's going to give you 10.1 grams Al2Cl6. But test the other reactant as well. So 5.40 grams of aluminum is certainly less than 8.10, but you still need to check it because those ratios are different. So 5.40 grams aluminum, turn it into moles using molar mass of aluminum from the periodic table. 2 moles of aluminum, 1 mole Al2Cl6, and multiply it by the molar mass, 26.6 grams Al2Cl6. Now at this point, you've got 2 amounts of product that are made. You want the smaller one, and 10.1 is certainly smaller than 26.6. So what that tells you then is that the 10.1 grams, that's the theoretical yield of aluminum chloride. That's all the Al2Cl6 you're going to make from this. Now the aluminum wants to make more, but you're going to run out of chlorine first. So chlorine is the limiting reactant. It's limiting how much product, how much Al2Cl6 you can make. And the other reactant, in this case aluminum, that's called the excess reactant. You're going to have aluminum left at the end at this one, and it might be a good idea to know how to get rid of it if you're trying to purify Al2Cl6, or maybe you can lower the amount of aluminum in your reaction next time. So let's say your boss is looking over your shoulder and your boss says, hey, how much excess reactant aluminum is left at the end of this reaction? And your boss might be interested because if you can use less chemicals, it's less money up front. That's a good financial reason. Less chemicals, less money. All right. On the other hand, environmentally, it's good too, because a lot of times the excess reactants are just trash put into a waste stream, put into like a hazardous waste container. So if you can use less aluminum, it's better for everybody. It's better financially, it's better for the earth, etc., etc. Well, now that we know the chlorine is limiting, you can use grams to moles to moles to grams and figure out how much aluminum you actually needed in this reaction. So similar to last time, we're going to start with the limiting reactant, chlorine. Grams to moles to grams is the dance. So grams chlorine to moles of chlorine using the molar mass. But now notice that we're going from moles of a reactant, chlorine, to moles of another reactant, aluminum. So there's a 2/3 ratio. And then for every mole of aluminum on the periodic table, it's 26.98 grams. So we're going to turn moles of aluminum back into grams. And it turns out 2.05 grams, that's the amount of aluminum we actually actually needed to make this reaction happen. Now we put 5.40 grams in, so if you subtract how much was actually needed, 2.05 grams, you only really needed 2.05 grams. That means there's 3.35 grams of unused aluminum, all right? Now sometimes in chemical reactions, chemists will put an excess of one reactant in, and we'll talk about this during Chemistry 223 and something called Le Chatelier's principle. Don't worry about that right now, but as long as you can figure out how much excess you have in there, it might be nice to at least consider moving it down, using less aluminum next time or something. But again, there are some chemical reasons why sometimes you will use excess amounts of reactants. That's for a future lecture. I have so many things to show you, but at least you can calculate then the amount that was actually needed, and you can also figure out then the amount that is in excess and unused at the end of the reaction.